Hello, welcome to the module theory course. And so in this course, we are going to discuss about modules and many other things related to modules. So I'm Mehdi from the math department of the FEPME. So actually what we want to do that in this lecture, let me show you and share with you with the slides. But usually I'm not only follow the slides, I'm trying to writing some proofs, but I put some things in the slides because I want to save your times and my times also. So compendium. So actually what you want to do that in this lecture, first lecture, we want to discuss about definition of the left R modules and right R modules and examples. You will see many examples related to left R modules and right R modules, and we will compare each others. What's the difference between left types and right types? Then we will discuss about some basic properties of the modules, and maybe some of them is familiar with you, but we will try to gather in all of the material because we are studying it related to module theory. So, and of course, we will discuss about submodules. Submodules actually related to some vector space. Actually, we can say that modules is generalization of the vector space, and we will see that why. Then at the last part of this lecture, we will learn direct sums and direct product of the modules. So well, so let me start. So the concept of the module is an extension of the concept of the vector space over field. So modules are defined over arbitrary rings. So let me define a left R module. Okay. So actually, let R be let R be any ring with or without unitary and commutative or not. It doesn't matter as a it would be considered that the commutative ring or not commutative ring, or your ring belongs to one or not. So later we will consider that some subcases, some special module have it, and we entitle some names to them, but right now for general case, no, we will not consider. So, okay, so the definition, okay, actually an abelian group like M with the addition is said to be a left R module or left module over R if there exists a map from from R times n to m, and we denoted this map by this notation. We consider that one element from R ring and one element from this group, and it's like multiplication. Actually, we have seen this before in the vector spaces, and we call that is a scalar multiplication or a structure map such that uh, the following three conditions. So which conditions? So you see that the first condition is a times x plus y, which is equal to ax plus ay for any a belongs to or ring R, and for any x and y belongs to M. So the second condition, a plus b times x, which is equal to ax plus b for any a and b in O ring and for all x belong to M. And the third condition is ab times x. It's like associativity property, which is equal to ab times x for all a and b belongs to R and for all x belongs to actually M. Let me emphasize more. If you see that we say that it's left R module, okay, so it means the element from O ring, it's come from the left, and the element from actually this group is comes from M. You see that it's we multiply from left hand side, okay, to M. So M actually we consider that M is a module, and actually it would be from left hand side we product by the element of our ring. So that's why if you see that all of the element from the ring, it's considered that from the left hand side to right hand side. You see A times X plus Y, A plus B is again is the element of actually our ring, and X element of our module. And also here, if you see that everything is act from left hand side. Okay, so the map is actually not a scalar multiplication map, and as I said, so if you observe this condition or some kind of the vector space condition over any field, so actually we know that the any field is a kind of the ring with a more spatial properties you add, I mean it has any fields, so that's why we can say that any vector space is a module, but reverse of that is not satisfied. So let me talk about some one more definition in next slide. So we want to talk about unitary left modules. As you see that first condition we mentioned that it doesn't matter our ring is a unitary ring or actually it's commutative or not, but in this case we consider that our ring has one. So let's define it. Okay, a left R module like M is said to be unitary left module over R. It's actually where R is a ring with a unitary and denoted by 1, as I told you. And if 1 times x, I mean if you multiply by 1 to any elements of the module, it's for any elements of the module, it would be again x. So this is extra condition, as I told you, it's x scalar multiplication 1 times x should be equal to x. So now let's see some see various examples. So now we want to check some, I think 7 examples in this part actually. So the first example, let R actually be any ring and let I be any left ideal. So then I is a left R module. So this is the very clear from the definition of the left R module. So, and we are familiar with the definition of the ideal. Actually, it would be a subset of the ring such that based on the operation, operation, it should be a subgroup of R n plus, and by multiplication it should be loose. So, but in this case, actually we say that left ideal, we can only multiply by the left. So maybe if you multiply from right hand side from the element of the ring, so maybe it's not include and belongs to I. So now let's discuss about second example. Okay. So now we want to talk about second example. I mean, second one, the ring R itself is also a left R module with the scalar multiplication, just the multiplication of the ring. So actually we know that each rings itself also is a actually is a ideal. So that's why maybe we can think, but it is a very trivial example. You see that the scalar multiplication, it would be like here. So the any ring R is a left module over R with the scalar multiplication defined as, so let us say that R times R, it's goes to R. So you can say that it's all of the element it's selected from the O ring. So just take AX going to AX. So this is a simply the multiplication in R because it is a ring and it as addition as well as multiplication. So with this structure, R is always a left R multiple. Let's go to the next interesting example. Okay. So example 3. So this is the unitary Z mode. So Z, I mean, is the ring of the integers. So the unitary level Z modules are simply abelian groups. So let me prove that. Let me change a slide. Okay, very good. Just a second, let me change my place. I need more space. Very good. Let me select some nice color. Okay, I like this color. So, actually, let me take an abelian group. Okay, actually, let M be any abelian group. So let M be any abelian group. So they define the structure map. Let me define the structure map as follow. So it would be, we define the structure map. Let me change the color. It is the left R module. That's why it would be Z times this guy goes to M. Then actually we can say that N X goes to Nx when for any natural numbers, actually, the integer numbers. So define as if you take any n in the z and if you take any x in m, so this is going to nx. So, but how is this nx defined? Okay, let me define that as follow. Oops, just a second. Sorry. Okay, we consider that, okay, nx, which is equal to um, x plus x plus x n times when actually n is a non-negative integer number and minus x plus minus x when n is a negative integer number. So, and n times actually we need to add these guys together. So what can we do? So let me again be in my board and then I will come back to you just when I want to save your time. So we claim that, and we want to prove that claim. Actually, with this structure map, with this map, M plus is a left R module. So, and we no need to verify all of the three conditions. So let me check that with my pi because we are beginning and it's not bad if we are trying to do some things together. So the first condition, I mean, we can say that for actually natural number is z, sorry, integer number in z, and x and y in the M. So we know that M is abelian group. So right now we want to check this guy. It's okay. So n times x plus y. So it means you, based on this definition, n times you adding x plus y together. So x plus y plus x plus y n times. So it's according to our definition. What is this? Actually, it's we are adding n times. So what we do this, it's since R in an abelian group, we can write like this, and we can separate all of the x's, and plus we can separate it all of the y's, whatever way order does not matter in the abelian group. So this is the also n times. So I mean we can write like this and separate them because we are going to abelian, working in abelian group, and they are also n times plus y, and all of the disguise is n times. I mean n. Oops, just a second. 1 times, 2 times, and 3 n times, and also here it's n times, and n times you are adding the y's. So we can rewrite that as a nx plus ny, and the first condition actually it would be, therefore the first condition is done. Now let me raise and write the second condition. Now if you look at the second condition, so second condition, so for m and n, for m and n as integer numbers, and x in the abelian group m. So let's look at m plus n times x, m plus n times x. So this is x plus x plus x. It's m plus 1 times. So actually it would be x plus x, m plus n times. So, okay. So then this is the nothing but adding. Actually, you can say that, or I can say in just a second. Let me, I'm freezing my board. So now based on that an abelian group has associative property, we can separate actually x plus x m times plus x plus x n times. I mean, for this guy, it's m times. And for these guys, we have n times. So generally, we can say that it would be m times x plus n times x. So this actually, and this means that second condition also done. Let me work on the third condition. So now third condition, so m times n times x. You wanna check that. So let's just look at this one. So this means we are adding x, m, n times. So it means x plus blah, 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 x, m, n times. Okay, so what's the trick we can use it? It's easy. So that is x plus x plus x. This is m n plus times. So this means x plus x. So this is we are doing n times plus x plus x again n times plus and so on. So this means also n times. So I mean we can say that it's x plus x plus x plus x. Each box is n times, actually n times, and the number of the box, actually it would be n m times, so it would be box 1, box 2, and box m. So I mean it would be, if I want to write more compact, it would be nx plus nx, so it's m times. So actually right now we can say that it should be, just a second, it would be m times nx. So therefore all of the three condition we are done. Now last condition, it's we want to check that unitary. So let me check that. Let me erase everything. So now last condition is, it is clear that 1 times x, which is equal to x for all element in abelian group M. So thus we can say that, then we can say that, then we can say that M is a left Z module. Okay, so if we start with an abelian group and we have shown that it has a left Z modulus structure, then therefore it's a left Z modulus. Now let's do conversely. So let me erase everything. Okay. So conversely, what we want to do that? Converse. Okay, let me write that. Okay, very good. Actually, let M is a left Z module, okay, with the structure map with the structure map. Let me change the color. Z times n goes to m, and n x goes to nx for all n in the z and for all element in ring in the module. So we want to show that show. Okay, we want to show that n times x, which is equal to nx. So for all n and for all x in the module. So let's do it. So, okay, let's look at the n times x. It can be written as, let me write this, just a second. N times, oops, n times x, it can be written as, okay, it would be 1 plus 1, blah, 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 1 times x, if actually n is greater than or equal to 0. And this is minus 1. Actually, it is n times. Minus 1 plus minus 1, blah, 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 minus 1. And actually n times x. So if n is a less than 0, so it's good. It's good. So far, so good. So by using the property of the module, so then we can say that, okay, I can write here, instead of here, actually I can say that it would be, let me write with another color, 1 times x plus 1 times x, blah, 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 1 times x, okay, so when actually n is greater than equal to 0, and here we can say that it is equal to minus 1 times x plus minus 1 times x, blah, 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 minus 1 times x when n is a less than 0. So then with 1 times x is the same as x. So I mean, we know that is a unitary. Actually, let me write with another color. Okay, very good. So let me write my yellow one. Okay, so it is a unitary, and this guy which is equal to x, this guy which is equal to x, and this guy which is equal to x. So in this case, we can say that it would be x plus x blah 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 plus x. So when n is a greater than 0, equal to 0 and greater than 0. And in this case, we can say that each case it would be minus x, and minus x. So in both cases, we can say that it's like actually n time nx, and this is also nx. So this means it's precisely nx, and as we want, and it's also an abelian group, and therefore we are done. So actually, it's done. Perfect. Let's go to next example. So if R is a field, and then any vector space over R is a left R module, so this is the clear. So now let's, actually it is very clear. So for example, if R is a real number, for example, real number field, so then any vector space over the real numbers is also a left R modules. Actually, we'll see that later in this case also. It would be right R modules when we learn what is a right R module. So let me more interesting example. So let's look at the m by n matrices or any ring. So let R be a ring and let m index m times nr. I mean this notation. It should be the set of all of the m times n matrices when A is an m by n matrices. So it's entry coming from the ring R. So now we know that this guy is an abelian group with respect of the matrix addition, and it's left R module with this structure math we define as well. Let's suppose, I mean, it's like a scalar multiplication to a matrix. I mean, shortly, it's briefly, I will tell you what I mean. For example, let's suppose your matrix, it would be, for example, this guy, 1, 2, 3, 4, and the ring, it would be ring of integer numbers. I mean, R, which is this guy. So, and we consider that, for example, -1 as an element of integer ring is A. So in this case, A times A, it means -1 times A. It means you need to only write the additive inverse of each element. So -1, -2, -3, -4. That's it. So it would be, actually, it's also, this is also m by n matrices, and with respect this scalar multiplication of matrix, it is an R module. So now let's come to the next example. Okay, still we have some examples. So maybe one more examples also. Okay, let R be any ring, and let us take M, which is equal to, I mean, the polynomial with over ring R in the variable X and Y. So with the coefficient coming from actually the ring R. So then it's clear that M is a left R module. Addition is addition of polynomial, and multiplication is just usual meaning of the multiplication, that is the polynomial multiplied by with a constant. So let me explain a little bit one more. So for example, let's suppose R is an integer numbers, ring of integer numbers. So, and we can say that M is a Z, X, Y. So it means, for example, F and G, they are element of Z, X, and Y. For example, let's suppose F, it would be like this. For example, oops, let me write like that, just a second. F of X, which is equal to, for example, 2xy plus x squared, and gxy, which is equal to x squared plus 3y. So actually the addition. So I mean, we can say that also this guy, z, oops, what I'm doing, okay, z, x, y with addition, it would be an abelian group. So you know how we can add these two guys. So it would be f of x plus y. Oops. Again, I'm doing some strange things. I don't know why. So which is equal to, okay, we have one guys like this. It has variable x and y with degree 1. So we have 1x2 here. It would be 2x2, and it would be 1 free y. So free y. So it's the multiplication, and therefore a scalar multiplication, for example, we can say that which a, which is equal to, for example, 2 as an integer number. So a times f, which is equal to 2 times, for example, here it's 2xy plus x squared. So, and you know that what's going, so I don't need, it doesn't need I wrote that. So let's go to next example. So let R be any ring. So then let's look at the R2. It's like more abstract stuff is we can assign to Cartesian plane. So in the Cartesian plane, R is a ring of real number. Real number is a field, so any fields are real. So in this case, it would be the plane, but here is we have more abstract stuff. So and then this is the set of order tuples like A and B, and you can see here such that A and B they are element of our ring. So then R2 is a left R module with a scalar multiplication. It's like the addition of actually two vector in R2, and the scalar multiplications actually two vectors. So it's like a staging and something like that. So we know that actually R2 is an abelian group with an usual component-wise addition, and we know that from R, it's also here is like a similar way. So the scalar multiplication is defined as take any element like A in R and take xy in R. Oh, sorry, here is typo. I must write x and y. Okay, sorry. So just define A times x, the order xy is would be A x times A. So with the respect of to this is x, actually with respect to this scalar multiplication. So this is LFR model. So that's it. Let's go to other stuffs. Okay, now we will discuss about some basic properties of R modules. I mean R left modules. It's majority of them are familiar for us, but let's see what you want to do that. Okay, so before that, let's fix some notation. I mean, let M is a left R module, and then 0 with index R is the 0 element in R, and 0 index M is the 0 element in M. So sometimes we don't need to write the index of zeros, but right now we want to use simultaneously both of them. That's why we need to make a difference between them. So, okay. So let me start with the proposition. So let R be a ring and M be a left R module. Then the following are true. I mean, so 0 R times X, which is equal to A times 0M. You see that we use simultaneously both zeros. So, and this is okay for R X belongs to M and A belongs to R. So, actually, so this is the first one, and second one it's minus parenthesis ax, which is equal to minus a times x, which is equal to a times minus x, and it's true for all a in R and x in M. So here minus means the additive inverse actually. I mean here. So, and the third one is m times n times parentheses a times x, which is equal to m times na times x. And it's true for all m and n integers and a in R and x in or module M. So let's prove it one by one. So let me prove this. I mean, the first one, these are easy verification only. So the first one, let's us look at 0 times x. Actually, we can write 0 r times x, which is equal to 0 r plus 0, I mean the 0 in the or ring, times x. So y is true because if I add any things to 0, we will get the same things because self is a identity element. So now this is equal to, by distribution law, we can say that which is equal to 0 r times x plus 0 r times x. So finally, then what we have r times x, which is equal to, sorry, 0 of r times x plus 0 of r times x again. So I didn't write in the middle part. So and now if we know the cancellation rule, I mean if we cancel this guy from both sides, let me use my other color. Okay. So what will be happen? So in this case, so we will the left from right hand side, you have, and from this side you have 0m, and or we can write like this in just a second. So it would be 0 r times x, which is equal to 0 m. So this is 0 in m actually. Similarly, the other one also, you can do this like that. And just a moment, let me shift these things from the right left hand side. Now we will discuss about this guy. I mean, can say that a times 0m, again with the similar argument, a times O0, or I mean 0m plus 0m. So which is by distribution law, we can say that a times O m plus a times 0m. Doesn't matter. Sometimes I can say that is 0, or sometimes say that. So this is the further can we write that actually it would be, then here with the same argument we can say that it would be 0 a by cancellation route, a times 0, just a second, a times om, which is equal to 0 of m. So you see both of them, this guy and this guy, both of them, they are 0m. So this is finished in the first one, and so let's go to the proving the second one. So for the second one, we started from this guy, and we will see that we can minus, just a second, minus a times x can be written as minus 1 times a times x. So this is further can be right like this. Just a second. Minus 1 times a, because a is from the ring, and this guy times x by the using property of the module. So then actually this is precisely which is equal to minus, oops, I forget to write one here. Okay, and this is precisely, it's equal to minus a times x. So, and this is exactly minus 1 times a times x. So, which is equal to actually, or I can say a times minus 1. So, just a second, let me, okay. So, it's a times minus 1, because the identity element in the ring can commutative. So, oops, times x. So this is again multiple of a times minus 1. So we can rewrite that a times minus 1 times x. So, and finally, we can say that it's actually because where one it belongs to R, and we need to assume that the uh, actually it's working. So then this is equal to a times minus 1 times x, and this is equal to exactly a times minus x. So from here we got here. So actually the this finishes too. So let me put the UED. Let's go to last one. So again, let's start from the left hand side. So what does it mean? M N actually times A X. So this means, let me write from just a second. Okay, very good. Okay, so I will write from here, and then I will write here, and I will say that at the end it would be equal. So Mn times AX. What does it? It means actually you Mn times you adding AX. So it means AX plus AX plus AX. How many times? Mn times. Very good. So we can actually take a common, and you see that it's a is a common from all of them. So we can say that, okay, which is equal to a times x plus x blah 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 x. So again, mn times. Okay, so right now we can say that this cut is mn times, so we can write that finally as we want. Okay, a times m n x. Okay, this is the left hand side. All right, now you want to work as a with right hand side. So what does it mean? M N A times X. Okay, it means you just a second. It means you're adding A. Okay, first of all, you're adding A, then times X. But how many times you have A? M N times. So right now, if you distribute A to X, so you have AX plus blah 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 AX. How many times? Mn times. So it means finally, which is equal to Mn. Oops, we can, doesn't matter. Mn AX, because we have Mn times AX. So therefore, all of are equal. So you can see that. So you can see that all of them are equal. And then, so this finished the proof of the properties, the proposition and or property, basic property. So you see that these properties also we have already in vector space and the rings also and so on. So we will see that later why you were familiar with them, because any ring and any fields, they could be a module, and I mean left or module or right or module we will learn in these lectures. So anyway, let's continue. So and now let us define right our module. So let's see what's happened. So in a similar way, it will be go how we define the left R module. So let R be any ring, okay, and it doesn't matter, it would be commutative or not, and unitary or not. So, okay, an abelian group N with addition operator is said to be a right R module or right module over R if there is a structure map like that. So, and denoted by X and A, which is equal to, and actually to XA. It's called a scalar multiplication or a structure map such that, okay, such that the following three condition hold. So you see that before, it's the right, and that's why you see that the element from the multiplication is in the right, and you see that A is a right part of the element of the OR module. That's why we say that is right OR module. And left hand side, left R module it would be from multiply by the left hand side. So the first case, in the first condition, it's x plus y times a, which is equal to xa plus ya for every a in our ring and for all x and y in our module. So an x times a plus b, which is equal to x times a plus xb. You see that all of the elements from the rings would be in the right hand side for all a and b in the ring and for all x in our module. So an x times ab, which is equal to xa times b for all a and b in our ring and for all x in our module. So the similar condition, but according to our scalar multiplication, we have these three conditions, and for the definition, we want to discuss about unitary right mode. So suppose again R has a unitary. So if one, it's actually if one belongs to R, then the right R module M is said to be unitary if x times a, which is equal to x for all x belongs to M. So now we have two type of the notations, and one is a left module notation and another one is a right module notation. So then whether they are the same or different, so studying about actually studying about all the left modules over all the ring is the same as studying all right module over all rings. So let me remind you some remarks. Okay, so first of all, studying about all left modules over all rings is equivalent to a study about all right module over all rings. So it means by symmetry, I mean, it's without losing generality. It's only we discuss about after we see some example about right arm modules. Only we are discussing about left arm modules usually. So okay, and one more remark. Okay, if R is a commutative ring, then every left R module is also a right R module and vice versa. Let's prove it together, and it is the simple only. So let me start with the left R module. So actually, we know that we are right now, we want to consider that R is a commutative ring, and also actually we have a one module. It is a left R modules, and we want to prove that it is also a right. And then after that, in this another direction, we consider that R is a commutative ring. Also, M is a right R module, and we want to prove that it would be also left R module actually. So okay, let actually let M be a left R module. Okay, with the structure map, with the structure map R times A M, and for all A and X is the best some definition of AX for all x, sorry, for all a in R and for all x in M. Okay, very good. So far, so good. So now let's define another map. Okay. We define another map. Let me change the color. Oh, it doesn't matter. Okay, let me define another map like M times R M. Okay, from X and A goes to XA for all A in R for all X in M. So, okay, and I'm just using this notation. So let's actually define XA. Actually, as you see that everything is right now, we have to kind of the multiplication and okay. So actually, right now we can let's define this guy. I'm defining so this guy which is equal to this guy because they are in the ring and ring is a commutative. So and here AX is a left orbital structure scalar multiplication. No, right now we have one claim. Let me moving this guy. Just a second. Okay, we have one claim and we want to prove that. Okay, what is our claim? We want to claim that. Okay, what is our claim? M is a right R module with this map. I mean, we define. Okay, so what can we do? Actually, we can say that for X and Y. So let's check. Okay, the first condition, we want to check that for X and Y in the left arm module M and A in O-ring. So we have this assumption. X plus Y times A. We want to prove that. We don't know. It's like X times A plus Y times A. Okay. Let's do as following. Okay, let's suppose we have X plus Y times A. Okay, we know that O-ring is a commutative and X plus Y and A, both of them, they are in O-ring. So that's why we can write that A times X plus Y. Okay, and right now we know that, and here it's based on, I can say, it's this property, I mean, it's the commutative. Okay, right now we can write like a times x plus a times y. Why? Because m is a left arm module. Okay, so it's m is r, actually m is left r module. Okay, very good. So, okay, right now what can we do? Okay, right now, again, we know that this guy is in O-ring, and this guy is in O-ring, and O-ring is commutative. Again, based on this assumption, R is a commutative. So each of them can be, instead of AX, you can write XA. Instead of AY, you can write YA. So right now, so this is exactly as we want. So from here, we could obtain this here. So that's what I mean. This guy is the first condition is satisfied. So let's go to the second condition. Let me erase everything. Okay, the second condition of R, right R module. So we want to show that for X in M and A and B in O ring, actually X times A plus B, which is equal to X times A plus X times B. Okay, again, we are starting from left hand side. Okay, X times A plus B. Very good. So because we are working in the commutative ring, you can change the place of X with A plus B. So we can write A plus B times X. So because R is commutative, so very good. But right now we know that R is a left R module. So that's why we can write A times X plus B times X. So right now we know that, here it's R is a left, sorry, M is R left module. Sorry, in the last part I also had this typo. Sorry. The 2 minutes ago we must say M is a R left module. M is R left module. So okay, and right now again the ring is commutative, so we can say that here we are in the R, so that's why we can say that X times A, and here again we are in the R, so we can write X times B, and we obtain as you. So here, so this is again is, let's check that the last condition. Now for actually X in M and A and B in O ring, we want to see that, okay, x times a b, which is equal to x times a times b. So let's start again. Let's start. Okay, we know that x times a b. Okay, so right now, based on this defined already, we are working in commutative ring. We can start commutate between x and ab. So we can say that which is equal to ab times x. Okay, right now, also a and b, they are in our ring, so they can be commutative. They can be commutative. So right now, okay, based on assumption, so we can write like b times a x. So right now, again here, we can use this fact. So we can write that a x times b, because this is again is one guy is from the ring and this guy is the one guy in the M because of this multiplication rule. So right now you can again, let me put point A. So right now, oops, just a moment. Okay, A, and here you need to put point X point because you want to use this max. So right now we can say that X and A, they can be commute because they are in the, actually based on these rules. And it's commutative also, it's more strong. So anyway, X times A times B. So then it's proof from here, you then here. So then we can say that the claim is true and M is a right R module. So, okay, very good. So, yeah, so they satisfy all free condition. So, we can say that M is a right R module. So, now let's look at various examples. Okay, so the very first example is any ring R is a right R module. So how is the structure math defined? So this is the simply R times R goes to R with, you see that is the multiplication, it's from R and again. So it's a very trivial example. So we can verify that it is a satisfies all the conditions. So then this is the fine. So let's go to the next example. So suppose that let is a contained in R. So suppose that S is a subring of R. Then R is a naturally a left and right S module. So let me a little bit discuss with you, a little bit only. So for left, left module and right module. So you can see that it's the scalar multiplication or a structure map. It would be like this, and from ax goes to ax for, and this is the multiplication actually in R. So we consider that for all A in S, and you know S is a subring of R, so that's why it's the same multiplication in R here. So an X is in R. For here also it would be similar, but the multiplication is from right hand side. So it would be XA maps to XA. So again, this multiplication is in R because, and here also. So that's it. So how it is naturally left and right S module. So for the left module, the structure, let's also look at this multiplication and see that. So it's again, it's the same multiplication. So let's go to the next part. So you see that, as you see. Okay, now I'm going to discuss about submodules, direct sum and direct product of the modules, and we will see some examples also. And let me continue. So I'm discussing about the submodules, direct sums, and direct products of the module. So let me start with the definition of submodule. Okay, so let R be any ring and M be a left R module. So, okay, the non-empty subset N of M is said to be a submodule of M if the following condition hold. The first condition is N with addition is the additive subgroup of M, and M with addition operation. I mean, subgroup additive is additive group. So, and also N is a closed under a scalar multiplication. It means for A belongs to R and X belongs to M, then AX is belongs to N. You see that it's the left R module, that's the multiplication is from the left hand side. So we have so many examples I will give to you. So first example, that R is any ring and I containing R and is any left ideal. So then I is a left R module of R because we know that R is a left R module naturally, and is a trivial example, and the scalar multiplication is the multiplication in the ring R. And if you take any left ideal, so this is the always is a left R module and it's a submodule of R. So what about the second example? So second example, suppose if M is a any left R module, then if you look at the singleton 0, so the additive identity, I mean, which is always sitting inside of the M, is always a left submodule of M known as a 0 module. So singleton 0 is satisfied all conditions of left R module, and since it's a submodule, so submodule means that it's it is itself is a I mean that it is itself a left arm. So let me go to the next definition. Okay, so which is the direct product of the left modules. So let me start with a ring and let R be a ring and M and N be left R modules. So let's take M and N. Actually, both are left R modules. So let's look at the Cartesian product of M and N, which you already know that and denoted by this notation. So, okay, and this can be made into a left R module, which is the scalar multiplication. So the scalar multiplication defined in this way, like here. I mean, the scalars come from R, and here is come from or module or left R module would be this. I mean, here instead of the same, I mean, elements we have the pair and or module is as the shape of that is would like a pairs. So if you take any elements and A, okay, from the R, okay, and pairs like X and Y, so you have this multiplication. So for n A in R and X in M and Y in N. So by using this 1M and M times N, I mean the Cartesian product of Mn, satisfies all condition of the left R module. So this is known as a direct product of M and N and denoted by M times N. So the usual way. So let's go to next part. So similarly, we want to generalize that. So similarly, for any family of left R modules, we can define the direct product. So let's see how we can define. More generally, the direct product of a family of left R modules, let's say that the family is like this guy, I mean M index alpha, and alpha belongs to the some index like I, and this index set I can be finite actually. So, or also infinite. So it doesn't matter. Also can be countable and can be countably infinite or infinite also. So the direct product of the family of R module is defined as the left R module M. So, and it should be like this. So M, which is equal to product of M alpha. So this is the direct product, it's just a notation. So here the scalar multiplication, it would be R times R to R. So how can it define actually? So first of all, how does the element of M look like? So there are like this guy, the element of this M. So when alpha belongs to I and the infinite tuples or means the tuples indexed by I. So this is the typically an element of M, and if you take any element in A in R, like here, so if you look at the scalar multiplication, like A times this guy, so as you see that is a kind of in matrices also it's we did like that. So it's A times X alpha, so this is defined like this. So of course, here X alpha belongs to M alpha, and for every alpha belongs to I, so it means the component wise scalar multiplication. So each component of M alpha, we are component wise multiplying A. So this is satisfy all conditions of left R module. So therefore, M is a R module known as a direct product of the family of MA of left R module. So we can see many examples. So let's go to checking examples. So okay, and we can discuss about we can take a various index set. So suppose let's ask the first R times R. So this is the Cartesian product of the R with R. And so this is the a left R module. Sometimes we can take in more general case, I mean the product this guy is n times. So then this is also a left R module. This is the Cartesian product of n copies of R. So also we have more general case. So we can actually we can have infinite copies also. So for example, m which is equal to product of the the indexes come from the natural numbers. So we have infinite tuple. So this is the direct product of the Cartesian R index alpha. Alpha belongs to let us to say that the natural number, as I say that, and when R alpha, which is equal to R, so all of the case we consider that R alpha is the same. So R is a ring. So this is an example of various Cartesian product of modules. So, okay, now let's look at two new concepts. So now let's come to some of more submodules. So let's go to this definition. So let M be a left R module where R is any ring. So it means M is a left R module. So, okay, definition. Let P and Q containing R, M be two submodules of N, then the sum of P and Q is defined as follow. I mean P plus Q. As before, we try to generalize for some more generalized cases. So let's look at the set of all x plus y belongs to P and y, I mean x belongs to P and y belongs to Q. So this is the PQ is defined like this. So it is the clear, this is the subset of the M. And because P and Q are the submodules of M, so therefore they are subset of the M, and therefore P plus Q is also subset of M. So also clearly P plus Q is a submodule. Again, this guy is a submodule of M. So because it's a satisfy all the condition, so a scalar multiplication is the same as the scalar multiplication coming from M. So it is a submodule of N, and therefore it is known as the sum of the module of the P and Q. So let's generalize that. Okay, so more generally, the sum of the family of submodule like M alpha, I mean there are several submodule of M, where I is a sum index set, so defined as a follow. So you can see that it's the summation of blah 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 and belongs to M alpha for all of the alpha belongs to index, and it's after x alpha, which is equal to 0, x makes finite many xi. So you can see that here it has this shape. So the sum we are considering are finite sum of only even tau I is an infinite set. So this is the basically something's like that. Okay, that is the set is the same as this. And of course, everything is sitting inside of M because each M alpha is a submodule of M. So then if we take their sums, that is also a submodule of M. Therefore, this summation is also the submodule. I mean, this guy is a submodule. As an exercise, not bad to check that. The submodule of M. So it is also a left R module. So one can check it is not difficult. It is a satisfy all the condition of the left R module. So it is a left R module known as a sum of the submodule M alpha. Okay. So let's go to the next part. Okay, and also the sum of the smallest submodule of M containing for every alpha is belonging to alpha. Anyway, I mean, this guy is a, let me write that. It's not bad. It's not or remark. This guy, I mean, let's call that M prime. M prime is the smallest submodule of M containing M alpha for all alpha belong to or index or index. So let's see some examples. Okay, so let's take the ring as an integer number and let's take P, which is equal to ideal generated by 2. So, and Q is the ideal generated by, okay, it's for generally, let me change a little bit the problem. I want to change this to from 4 and here to 6. Okay, so it doesn't matter. And the ideal generated by 6, I mean Q, and then let's compute P plus Q. Okay, very good. Okay, very good. So of course, P and Q are both submodule of R. So P and Q are submodule modules of ring R. Very good. So if I'm not writing anything, it's just simple. So submodule, this means that it's the left submodules, but let's skip that. So P and Q are both left R submodule of R. Let's compute what is a PQ. And PQ also, P plus Q, I mean P plus Q as well. So it's a submodule of Z, and here is Z, or in Z. So let's see what is this. So this is the ideal generated by 4 plus ideal generated by 6. So let me change my color. Okay, so it means P plus Q, which is equal to ideal generated by 4 plus ideal generated by 6. Okay, so what is this? So this is the basically, which is equal to 4 times A plus 6 times B, and A and B, they are comes from all green. So, but what is this set? So this is the simply an ideal generated by 2. That's it. This is the ideal generated by 2. That's why I changed that the first times. I mean, it's I consider that this guy as a 4, sorry, and this guy as a 6. So in fact, it's generated by the GCD of 4 and 6. So this is equal to GCD, greatest common divisor, of 4 and 6. So one can check that this is the nothing but 2, so it is ideal generated by 2. So let's look at one more example. So let's take again our ring is a integer number, and let's take an or module, it would be lattice. So M is a left arm module. Wait, okay, it is the left R module or left Z module. Okay, so and this is clear. So now let's us take P, which is equal to 2 times X and 0 when X is a integer number. It is actually, it is the, you see that what is the behavior of M? M, it is like X and Y such that X and Y, they are integer number. So it's very good. So far, so good. So, and Q, which is equal to 0 and Y which belongs to Z. So here both are contained in M, and check that P and Q are submodules of M. So, I mean, let me write that. This guy and this guy, they are submodule of M. So now let's come to intersection of the submodules. I mean, before that, I mean, let's compute what's a P and P plus Q. So what is that? So let's go to the next slide. Okay, let's do that. Okay, very good. Okay, so if you compute P plus Q, what is that? So this is the simply P plus Q, which is equal to 2 X and 0 plus 0 and Y. So an X and Y, they are integer. So now you have, if you this 22 X and Y, X and Y in Z. So one can check that this is also a submodule. So this guy is a submodule. So very good. So now let's go to higher things. You have one fact, you can prove it yourself. What is the fact? So No, it's let's come to intersection of submodule. So let M alpha be a family of submodule of N. And then we can say that the intersection of them when M is a left arm module. So this is also a submodule of M. So it is satisfy all the conditions of the submodules, and therefore this guy is a submodule of M. So now we want to look at the direct sum. So let R be a ring and let M and N be left arm modules. So and then, as we have seen above, the Cartesian product of just a second. So the Cartesian product P, I mean M times N, is a left arm module. So then P contain M and N as a submodule, namely N times singleton 0, which is equal to any element, the first component of them is X, I mean this arbitrary element from the module M, and second component it would be 0, and M times N when the first component is 0 and second component belongs to M. So M and N we can view as a submodule of Cartesian product of the P. And in the following way, M actually times 0 and 0 times N. So then the sum of these two submodules of P is called the direct sum of the M and N and denoted by this notation. So, I mean, if we can see that we have this notation, I mean, X and Y, I mean, the pairs, the first component, it would be X and second is 0 and reverse of that. So when X and Y is belong to M, and X belongs to M and Y belong to N, so we have this shape. So every element of M plus N can uniquely written as a sum of the elements of the in M and in element N. So, okay, so this is the, let me write one important fact here. Remark. It is, we have this in linear algebra also. So every element oops, just a minute. It's using my laptop. Sorry for interruption. So every element, of this direct sum can be uniquely written as a sum of an element in M and an element in N. Okay, we have this before in linear algebra. Okay, so far so good. And right now we want to talk about something relation between sum and direct sum. Very good. So we have one question. I mean, what does a sum become a direct sum? So I mean, what's the connection between them? So I mean, the sum is a direct in the following sense. Every element of the direct sum n can be uniquely written as a sum of the element of in M and an element in M. So I mean, we have this condition P, which is equal to actually M plus N, and M intersection N, which is equal to singleton 0. So that is the equivalent saying this one. So let's us prove more generally why this is. So this is because the following proposition, let me go to a proposition, I mean more generalized case. So okay, right now we want to discuss about this proposition. Let M and N contain in the P where submodules of LF are modules P. So then M intersection N, which is equal to singleton 0, and if and only if every element Z belongs to M plus N can be written uniquely as a Z, which is equal to X plus Y, where X belongs to M and Y belongs to M. So now let's see the proof. Okay, see the proof. Okay, I want to prove that by orange. Okay, so assume that right now we want to prove from this direction. So assume M intersection N, which is equal to 0. So let's prove this implication. So assume that M intersection N is equal to 0. So now let's take an element Z belongs to M plus N. So let's consider that Z belongs to M plus N. So we need to show that we can write Z uniquely as a sum of an element in M and an element in M. Now suppose that Z, which is equal to no, now suppose that Z, which is equal to X plus Y. So where actually X belongs to M and Y belongs to N. Very good. And now let's see the actually, okay, what will be happen. So now, and this has two sum. So let's suppose also, okay, you have another elements because you want to prove that uniquely. So Z also, which is equal to X prime, Y prime, when X belongs to M, X prime, and Y prime belongs to N. So, okay. So suppose that I have two such sums. So then we can say that, then we can say that X minus, because Z which is equal to Z actually, so then so that's why these two guys, it would be equal. So X plus Y, which is equal to X prime plus Y prime. So then we can say that X minus X prime, which is equal to Y prime minus Y. So they are in the intersection of N and Y. because it's actually this guy, it is in M. This is the module, M is a module. So this is inside of the M and this is inside of the N. So that's why we can conclude that these guys, they are inside of the M intersection N. So this means it's 0. So what does it mean? It means this guys, it should be 0. So it means, okay, let me take another color. So it means, okay, it means x minus x prime, which is equal to y prime minus y, which is equal to exactly 0. So this means, okay, x plus y, which is equal to x prime plus y prime. So it can be written uniquely. So uniquely is proof. So let me write another direction. So for another direction, we want to show that actually M intersection N, which is equal to 0. Very good. So let Z its intersection of, let actually Z is intersection of M and N. So then we can write actually Z, then can write actually Z, which is equal to Z plus minus Z, which is equal to 0. So this guy, and consider that this guy is as a element in M, and this guy is an element in N. So, okay, very good. So, and which is equal to, you see that you can write also 0 plus 0. But we have uniquely. So by uniquely, you can say that this guy is from M and this guy is from this guys. And also, it's at least both of them has 0. So we can say that also this is in M and this is in N. So right now by uniquely, we have Z which is equal to 0, Z prime which is equal to 0. So then Z which is equal to 0, and then we can conclude that M intersection N which is equal to 0. That's it. We have the same proposition in linear algebra. It's only generalized enough that, and we mentioned this guy and already it for, it's a very similar proof. Okay. So, and the proof is done. That's it. So thanks for your attention. See you for next lecture. Goodbye.